Let's start. Hello, everyone. Let's start today's workshop. I'm Keiji Saito, a chair for the first session. The first talk will be given by Takahiro Sagawa from Tokyo University. He will tell us about three approaches to quantum thermodynamics. Let's start.
Thank you for your introduction. I'm Takahiro Sagawa from University of Tokyo. Today, I'd like to talk about several aspects of quantum thermodynamics, especially focusing on three approaches to it, including stochastic thermodynamics and quantum many-body physics and the resource theory of thermodynamics. These three approaches are closely related with each other, but they have slightly different perspectives. So I will focus on these ideas and their relationship. Because this is a colloquium talk, I will start with a brief introduction or brief review to these approaches, and then I will talk about some of our recent results. Okay, so in modern quantum thermodynamics, there are many interesting experimental platforms. For example, trapped ions, superconducting qubit, single electrons, and NMR. These are small systems consisting of, for example, just one qubit or two qubits or three qubits. But there is a very big heat bus around it, so we can investigate thermal aspect of these quantum systems. So an important point is that we can observe both quantum and thermal fluctuations in these systems. So we can investigate, for example, the quantum fluctuation theory. And also we can directly perform measurement and feedback, so we can implement quantum Maxwell's demons in these systems. So it is important in terms of the relationships between thermodynamics and information. Also, there is another experimental platform called ultra-cold atoms. So this is a bit different from these other platforms because we can prepare many body system in the quantum region. I mean, for example, typically we can prepare hundreds or thousands atoms on optical lattice, for example, and we can control in a fully unitary dynamics of such a system. So this is a characteristic of ultra-cold atom system, and I will mention a closely related theory later. So given these very interesting experimental platforms, our theoretical approaches are, for example, stochastic thermodynamics. So this is the main target of this workshop, and the resource theory of thermodynamics. This is more quantum information theoretical approach to thermodynamics, and also quantum many-body physics. This is related to condensed matter physics. So today I will focus on these three approaches. And let me start with stochastic thermodynamics. I think this is the most relevant topic to this workshop. Okay, so as already mentioned in this workshop many times, the second law of thermodynamics is represented by the average entropy production. So it says that the ensemble average of the entropy production is always non-negative. So this is the standard expression of the second law of thermodynamics. Also, if we introduce the stochastic version of entropy production, we have the universal relation called the fluctuation theorem. So if you take the ensemble average of exponential minus stochastic entropy production, it always gives 1. So this is a very universal equality instead of an ordinary inequality. So, and we can also derive the second law of thermodynamics and the fluctuation dissipation theorem from the fluctuation theorem. So this is a kind of unifying equality of quantum thermodynamics. And the fluctuation theorem is valid in many setups from dissipative classical dynamics or classical Hamiltonian dynamics or classical Markovian dynamics. And also in the quantum region, this is valid both in the quantum unitary formation and quantum Markovian formation described by the Lindblad equation. So today I will first focus on the Markovian formation, and Then later, I will talk about the unitary formation. Okay, so this is my previous result. It is already 14 years ago. So this is about the fundamental upper bound of the work extraction from a quantum heat engine operated by a Maxwell's dam. In ordinary thermodynamics, the upper bound of the extractable work is given by the free energy difference. But if the Maxwell's daemon gets some information about the engine, then the upper bound of the extractable work is given by the information term multiplied by the Boltzmann constant and the temperature of the heat path. So here IQC is a quantum extension of classical mutual information, and the meaning of QC is classical quantum to classical mutual information, because in this setup the system is a quantum system and our measurement outcome is a classical variable. So this QC mutual information represents a correlation between the quantum system and the classical measurement outcome. And we can also introduce the stochastic version of the QC mutual information, and we can generalize the fluctuation theorem or the Jarzynski equality by incorporating the QC mutual information here. Okay, so this type of the generalized fluctuation theorem, including some information term, has been investigated in many setups. The simplest case is a single measurement and feedback in the classical region. And in this case, the information term is just mutual information. And its quantum extension is that I already mentioned. And the relevant information term is the QC mutual information. And also there is another interesting generalization of the classical case to the continuous measurement and feedback. In this case, the system is continuously monitored and the feedback is also continuously performed. This is very important setup because it is relevant to control theory by which we can stabilize or create a desired state of the system. And transfer entropy represents the information flow from the system to the sequence of our measurement outcome. So, and this is a classical case. And also in the quantum case, we can investigate the continuous measurement and feedback. And it is very important in real experimental systems to stabilize quantum systems. But the thermodynamics aspect of continuous measurement and feedback in the quantum regime was not investigated. So we have focused on this problem and derived the generalized fluctuation theorem by introducing a new information quantity that we name the QC transfer entropy. So this is the setup of our recent work. So there is a heat path here, and there is a system, and the system is a quantum system. And the interaction between the system and the heat path is described by the Lindblad operator. And also there is another measurement apparatus. And the interaction between the measurement apparatus and the system is also described by the Lindblad operator. And then we can define the QC transfer entropy. This is the quantum extension of the transfer entropy and also a continuous extension of the QC mutual information. So basically the QC transfer entropy is the accumulation of the conditional QC mutual information. And this is a very straightforward generalization of the classical transfer entropy, because the classical transfer entropy is an accumulation of the conditional mutual information. By using this quantity, we can derive the generalized second law of thermodynamics like this. So even if our measurement is continuous, we can show that the QC transfer entropy is convergent to a finite value. And also we can introduce the stochastic version of the QC transfer entropy, and we can derive the generalized fluctuation theorem of this form. So without this information term, the left-hand side is different from 1. This means the ordinary fluctuation theorem is violated. But if we incorporate the stochastic version of the QC transfer entropy, we always have 1. This means that the generalized fluctuation theorem is always true. We have also proposed experiment numerics hybrid verification method about this equality. So to verify this equality in real experiment, we need real experimental measurement and feedback, and we get some measurement outcomes. And in parallel, we need some numerical simulation to reconstruct the QC transfer entropy from the experimental data. So by using this method, today I'm not going into the detail of this, but by using this method, in principle, we can verify our relation in real experimental setup. Okay, so this is the first part. Then I will go to the second part, that is the quantum many-body physics. And next, I will talk about the relationship of stochastic thermodynamics and quantum many-body physics. First, let me briefly review this part. The basic motivation of quantum many-body physics in the context of the foundation of statistical mechanics is the problem of ergodicity. For example, we can consider this kind of many-body system with hardcore bosons. We can track the non-equilibrium dynamics of this system by exactly solving the Schrödinger equation by using numerical exact diagonalization. Then we can see that the expectation value of an observable goes to a stationary value after some relaxation time, and the stationary value equals the microcanonical ensemble average. Important point is that in this case, we don't introduce any dissipation from the outside environment, or the initial state is just a pure state without taking any statistical ensemble average. So it's just starting from a pure state described by a single wave function, and the dynamics is exactly uniform. But we can see the statistical mechanical behavior like the summarization to the microcanonical ensemble average. So this is very interesting observation because we have the statistical mechanical ansatz purely from quantum mechanics. We can also have the same kind of behavior in real experimental systems by using ultra-cold atoms or superconducting qubits. So the important theoretical idea behind this behavior is quantum ergodicity. So we consider the expectation value of an observable by a single wave function psi. Then after some relaxation time, it goes to a long time average, and the recurrence time is very long. It's typically the double exponential of the system type time and the system size, so we can ignore the recurrence. So then we can have the effective stationary state around here, and numerically we can observe that this long time average equals the microcanonical ensemble average. So the question is when this occurs. I mean, when and why the long time average equals the microcanonical average. So this is a question because now we don't assume any statistical mechanical ansatz like the microcanonical ensemble. So one important idea about this question is the eigenstate summarization hypothesis. So this hypothesis says that even a single energy eigenstate is already summed. In standard statistical mechanics, we have the microcanonical average, and that is equal to the summer average. But if this hypothesis is true, just by picking up single energy eigenstate, then its expectation value is already equal to the microcanonical average. And the strong form of the eigenstate summarization hypothesis says that this is true for every energy eigenstate, one non-integrable system. This is a very strong statement, but it is believed to be true from many numerical evidences for non-integrable systems under some reasonable assumptions like local interaction and translation invariance. Of course, there are some exceptions or counterexamples called quantum many-body scars, but I'm not going into the details. But at least for simple non-integrable systems, this eigenstate summarization hypothesis is true. And if this is true, we can easily show that the long time average, that is just a mixture of the single energy eigenstate average, equals the microcanonical ensemble average. So we can reproduce the ergodicity from the eigenstate summarization hypothesis. Okay, so this is a basic idea, and we can demonstrate the validity of the ETH by simple numerical simulation. For example, in this case, the system is just a XXZ model in one dimension, and the vertical axis is the expectation value of an observer, and the horizontal axis is NIJ eigenvalue. And in the case of the non-integrable system, this spread of points converges to a single smooth curve in the thermodynamic limit. So this is a manifestation of the ETH. On the other hand, in the case of the integrable system, this does not converge to a single line, but this variance remains finite, even in the thermodynamic limit. So this is the breakdown of the ETH in integrable system. Okay, so this is a very brief review of quantum many-body physics. So now let me go to our recent result that connects stochastic thermodynamics and quantum many-body physics. Our question is how to fill the gap between these two different ideas. One is the conventional fluctuation theorem, in which the proof is based on the assumption that the initial state of the heat bath is a canonical ensemble. And the canonical ensemble is a maximally mixed state and a fixed average energy. So the canonical ensemble is a very highly mixed state, and that is usually adapted in standard statistical mechanics. On the other hand, the eigenstate summarization hypothesis says that even a single energy state is summer without taking the ensemble average. So there is a huge gap between these two philosophies. So the question is it possible to understand how the fluctuation theorem emerges from quantum mechanics without assuming the conventional statistical mechanics like the Gibbs ensemble? And our result is that the fluctuation theorem holds even when the initial state of the heat bath is a single energy eigenstate, if the eigenstate summarization hypothesis is true. So this is our result. Okay, so this is the setup. We consider a very big heat bath that is a many-body system, and we consider a small system. And in the standard setup of the fluctuation theorem, we assume that the initial state of the heat bath is a canonical ensemble. But now we don't assume that, but instead we assume that the initial state of the heat bath is a single energy eigenstate. And the time evolution of the entire system is given by unitary evolution without introducing any external dissipation. And the entropy production is defined in a standard way. And in this setup, we have proved that the fluctuation theorem is true in the thermodynamic limit, in which the size of the heat bath goes to infinite. So, and our result is true both in the short and long time regimes. Here, the short time regime is defined in terms of the so-called Lee-Robinson bound, and the Lee-Robinson bound is gives the velocity of the information propagation from the system to the heat bath. And in this short time region, the information of the system doesn't reach the outer region of the heat bath. So in terms of the system, the heat bath cannot be, the system can distinguish the state of the heat bath. So if the ETH is true, the heat bath behaves as an effective canonical ensemble. So this is the idea of the short time region, and it was proved in our previous PRL paper here. And more recently, we have proved that also in the long time region, the fluctuation theorem is true if the ETH for the entire system is valid and we apply the rotating wave approximation. So we can say that in the entire region, the fluctuation theorem is true, even if the initial state of the heat bath is a single energy eigenstate. So this is our experiment numerical demonstration, and we can see that the ensemble average of this is always close to 1, and there is a small fluctuation, but if we enlarge the system of the heat bath, this fluctuation should vanish. So in the entire time region, the fluctuation theorem is true without assuming the canonical ensemble of the heat mass. I note that in our previous parallel paper, we observed a breakdown of the fluctuation theorem in a long time region, but it was from a kind of singularity of the initial state of the system that is called absolute irreversibility. So we now understand that without that absolute irreversibility, the fluctuation theorem is valid even in the long time region as well. Okay, so this is the connection between stochastic thermodynamics and quantum many-body physics. So now I'm going to the second approach, that is the resource theory of thermodynamics. Oh, by the way, I have written a book about this. This is a small book, but I have covered mathematical aspects of entropy, divergence, and modularization, both in the classical and quantum systems. So this is not only about resource theory of thermodynamics, but also covers stochastic thermodynamics approach to entropy and divergence. And the manuscript is in archive, but there are several mistakes still there. But in the published version, those mistakes are corrected. So and you can buy it in Amazon or Springer website. Okay, so the one important difference between the standard stochastic thermodynamic approach and the resource theory approach is the fluctuation of the work. In the resource theory approach, we usually assume that the work is a definite deterministic quantity without any fluctuations. For example, if the work state starts from a ground state 0, then it ends up with the excited state W with probability 1. So this does not include any fluctuation. So this is called a single shot scenario. And this is a kind of idealization of the philosophy that the work is a purely mechanical quantity and it should not include any fluctuations. And if we adopt this single shot scenario, then there is a second law of thermodynamics that is different from the standard second law in stochastic thermodynamics. For example, if we start from the given state here, and if we end up with the non-equilibrium state rho, then the work required for this state transformation is bounded by the Rényi infinity entropy, defined by this. On the other hand, if we start from the non-equilibrium state, and if we end up with the given state, then the upper bound of the extractable work is given by the Rényi zero entropy. So these Rényi entropies are different from the KL divergence, Rényi 1 entropy. So we have different kinds of second law in this single shot scenario. Important consequence of these two second laws is that the reversibility in thermodynamics is failed in this setup, because even when we make a simple cycle starting from the given state and returns to the given state, we need a positive amount of work that is given by the difference between S infinity and F0, even if we make the optimal protocol. So this is very contrastive to the standard thermodynamics, equilibrium thermodynamics, in which we can make a reversible cycle in the quasi-static limit. This means that there is no complete thermodynamic potential except for equilibrium transitions. Here, complete means that the state convertibility is characterized in a necessary and sufficient manner. So the question is it still possible to have a single thermodynamic potential S something that completely characterizes state convertibility in the necessary and sufficient manner in out of equilibrium and fully quantum situations? To address this question, we need some ideas from quantum many-body physics. And what we have proved in our recent papers is that there is a single thermodynamic potential if we consider a many-body system that has some reasonable properties. So our assumptions are like this. The state should be a spatially ergodic state. And here, spatial ergodicity is different from temporal ordinary ergodicity. And it states that the spatial average equals ensemble average. So this means that the fluctuation of any macroscopic extensive observer, like the total monetization, vanishes in the thermodynamic limit. And any macroscopic observer has a definite value, and there is no phase coexistence. So this is our central assumption in the proof. Also, we have assumed that the Hamiltonian is locally interacting and the translation invariant. Under these assumptions, we have proved that both of the Rényi zero entropy and Rényi infinity entropy are equal to Rényi one entropy. That is nothing but Kullback-Leibler divergence. Technically, we need some very complicated definitions for the asymptotic limits of these quantities. That is called information spectrum. But anyways, if we adopt a proper definition of these asymptotic limits, then we can show that both of the Rényi zero and Rényi infinity entropy are equal to the KL divergence. So physically, this means that the standard non-equilibrium free energy that is defined from the KL divergence serves as a complete non-equilibrium free energy that gives the state convertibility if and only if the work is greater than the free energy difference. So this is a very natural property, but it is quite hard to vigorously prove this for interacting many-body system. And we can now understand that there is an emergent thermodynamic potential for complete characterization of state convertibility under the ergodicity assumption of the many-body systems. And I would note that there's a similar result in a different setup. For example, we can consider additional system called a catalyst. That is an additional system that is basically unchanged after the dynamics, but we allow correlation between the catalyst and the system in the final state. Then in this setup, we can again show that there is a complete thermodynamic potential that is given by the KL divergence. So yeah, in summary, we can recover the complete thermodynamic potential in several setups where we consider the many-body system or we consider a very big catalyst that is attached to the system. Okay, finally, let me mention the last topic that I think is relevant to all of these three topics. That is the symmetry protected thermal equilibrium. So this concept is inspired by the ergodicity problem of quantum many-body systems. If we look at the thermalization process of an integrable system, then the long-time average is not equal to the Gibbs state, the canonical state, but instead it is given by the generalized Gibbs ensemble, given by this. This is a conserved charge Q. So this is a very natural extension of the Gibbs ensemble, but in the case of the integrable system, there are many numbers, actually an intensive number of conserved charges. So this generalized Gibbs ensemble becomes a very complicated system. But in ordinary integrable system, so these conserved quantities are commutable with each other. So our interest is about the non-commutating charges that are more inherent to quantum mechanical setup. And we wanted to give a resource theoretic foundation to the concept of non-commutative ZZ. And this topic was actually addressed by Nicole Juncker-Halpern and her colleagues in this paper, but we have adopted a very different approach to the same problem. And we have proved that the same form of the ZZ is the proper expression for the non-commutative charges. So this is our setup. Our central idea is called complete passivity. So this is defined as follows. If a state is completely passive, we cannot extract the work from multiple copies of the state by any unitaries, any cyclic unitaries. In the second law of thermodynamics, we cannot extract any positive amount of work from the system by any cyclic operations. But now we assume a stronger requirement that we cannot extract any work from any multiple copies of the system. And there is a mathematical theorem that states that only the Gibbs ensemble satisfies the completely passivity. So this is our starting point. And now our question is, what if we restrict the operation to symmetry respecting unitaries? Here, the symmetry respecting unitaries means that it is commutative with the total charge. And total charge means the sum of conserved charges of multiple copies. For example, in the case of the U1 symmetry, this is just a total particle number. On the other hand, in the case of the, for example, SU2 symmetry, this is the sum of spins for 3 directions. And we have proved that the completely passive state under the symmetry is always given by the generalized Gibbs ensemble of this form. Here, Q is a charge, and this can be non-commutative. For example, in the case of the U1 symmetry, this is...
Now you are entering the question time.
Okay, just a few minutes. Yeah. So this is a ground canonical ensemble, and N is a particle number. So this is more non-trivial and unconventional situation where we have spin operators as a conserved quantities, and they are non-commutative with each other. And in this case, we still have the same of the GGE in terms of the characterization of complete passivity. So this is a very simple statement, but actually the proof is very hard, and actually this is the hardest mathematical paper ever in my research life. So yeah, actually the proof of this theorem is very hard, and that proof was done by Yosuke Mitsuhashi. He is my student. Okay, so this is a summary. So take-home message is that the interplay of the 3 approaches provides rich insights on quantum thermodynamics, and entropy is always a key concept that connects thermodynamics and information. Okay, so thank you for your attention.